Welcome to my channel Maithili SK. So in this session we are going to continue with next topic, Hilbert transform pre-envelope and complex envelope of amplitude modulation techniques under unit 1 of EC 3491 communication systems. So in this session I am going to cover you about introduction of Hilbert transform. What is a Hilbert transform with respect to Fourier transform, comparison of both, then phase shifting systems and Hilbert transformation, frequency response of phase shifting systems, then Hilbert transforms and examples related with the Hilbert transforms, and what is positive pre-envelope and negative pre-envelope, and finally end up with complex envelope signals. So introduction. To start with the introduction, David Hilbert was the first person to introduce Hilbert transform to solve a special case of Riemann-Hilbert problem. So the Hilbert transformation is a mathematical tool that's used to analyze functions and signals. It is a linear operator that is used to create analytical signals which are useful in signal processing and communication. The Hilbert transform shifts the phase of every frequency component of a function by plus or minus 90 degree. Either it will be plus 90 degree or minus 90 degree, that is pi by 2 radians. It is used to create analytical signals which are useful for calculating instantaneous attributes of a time series. The Hilbert transform is a fast and effective method used to test for nonlinearity in a measured frequency response function. And it is used to test the nonlinearity, the same is repeated, in a measured frequency response, that is FRF. The Hilbert transform is used in signal processing to analyze real valued signals, and it is used in communications, particularly in bandpass signal processing. So previous topic we had studied about spectral characteristics of a signal with respect to FM, where time domain and frequency domain representation analysis of signal is represented. So the same is here when this transformation is a Hilbert transform, which is an effective for this nonlinearity analysis of a signal. So we'll be now comparing what is Fourier transformation and what is Hilbert transformation. So the FFT treats this amplitude versus time information. That is the fast Fourier transformation will be treating amplitude versus time information globally as it transforms the data to an amplitude versus frequency description. That is nothing but it is converting a continuous time signal into a discrete time signal in terms of Fourier transformation. That is, it is passed through the channel which requires a frequency component of the same. So x of t signal is converted into x of f. That is what they have told here, amplitude versus time in terms of continuous and amplitude versus frequency term in terms of x of f. Whereas the HHT is Hilbert transformation is not constrained by the assumptions of stationarity and linearity required for the fast Fourier transformation, and it generates both amplitude and frequency information as a function of time. So the Fourier transform property indicates that this complex heterodyne operation can shift all the negative frequency components of of t above 0 Hz. So in that case, the imaginary part of the result is a Hilbert transform of the real part. So this is an indirect way to produce the Hilbert transformation. So we'll be seeing it clearly here, how the phase shifting happens. So the phase shifting systems and the Hilbert transformations are explained here. Let x of t be the input to a phase transformer system and y of t be its output. So simply assume a system which is having a input of x of t and produces an output of y of t. So this system is called as a phase transformer system. That is, phase is being transferred. So the y of t is a phase shifted version of x of t. where all the frequency components are shifted by theta. That is, y of t will be nothing but x of t plus or minus phi, that is phase shifted version of the signal. So let x 0 of t be a cos omega t, and y of t be a cos omega t plus, that is a phase shifted version. So if we are giving a specific input, consider the specific input instead of this x of t signal. So here we are considering this as a cos 2 pi f naught of t, that is cos omega naught t, and here it is phase shifted version. So let's change the input frequency term. In other words, if it is taken as x1 of t term, that is a cos 2 pi f1 term, and what will be the corresponding output here is y1 will be the output. So in case of input being x1 of t, output will be y1 of t, which is nothing but the phase shifted version of x1 of t plus theta or phi. So here this is the phase shifted version. So the amount of phase shift is independent of the input frequency. There here frequency part does nothing with the input signal. So what will be the frequency response of the phase shifting system we will be seeing here. For x naught of t, if we are considering a cos omega naught t, the output y of t will be considered as a cos omega naught t plus some phase shift here, which is having the Fourier transform y of y naught of t, which is represented in Fourier transformation as y naught of f, that is a by 2 e power. This is represented Fourier transformation in frequency component will be represented in exponential format. So it is a by 2 into e power j theta del of f minus f naught plus a by 2 into e power minus j theta into del of f plus f naught. So what is the x1 of f? This x1 of f can also be represented in the same format of a by 2 into del of f minus f1 plus a by 2 into del of f plus f1. So what is y1 of f then, if we are representing x1 of here the same? So it will be in terms of exponential format of e power j theta into del of this component and the next frequency component with respect to plus and minus. So since the same is true for all the input frequencies, it is obvious that the frequency response of the phase shifting system will be represented with respect to e power j theta and e power minus j theta, which is for the frequency range greater than 0, and for less than 0 it will be minus j theta. So the Hilbert transform produces a phase shift of theta which is equal to minus 90 degree, and this considering for x of t, its Hilbert transform is represented as x h of t, which is a minus 90 degree phase shift, which is nothing but the phase 90 degree phase shift represented in radians is minus pi by 2. So the Fourier transformation of this hex h of t is nothing but hex h of f is given by the same above frequency term. Here instead of this we are going to represent it in x of h term, that is in terms of Fourier transformation, x h of f is nothing but e power j pi f j into pi by 2 into x of f is for frequency greater than 0, and e j pi by 2 into x of f for frequency less than 0, which is nothing but the signum function. What is signum function is nothing but we will be having the terminology where the frequency representation is like this. So instead of drawing the same, so this will be the signum function. So this is the signum function where you have studied in a signals and system, the basic signum function representation having the value for f greater than 0. This is your frequency and this is the frequency range for less than 0. So it will be contained here both. So this is the signum function. The Hilbert transform is also given by x h of t as f inverse of the given signal in signum function minus j into signum function of x of f, that is x of t complex there is convolution of 1 complex convolution of 1 by pi by t. So the Hilbert transform is also given by x h of t in terms of Fourier inverse functionality, and it is represented by the equation ranging from minus infinity to plus infinity when it is integrated with respect to lambda. Now Some examples representing our Hilbert transforms are shown here. So they will be giving an equation in terms of cos or sine and ask you to find what is the Hilbert transform of the given equation. So if here the case here is two signals are represented. So when it is represented in terms of Hilbert transform, for this case, how will you find the Hilbert transform? So solution here is, for this case we have to represent x of f and then find out x h of f. So the equation for finding a cos omega naught t is represented here, and what will be the x h of f is the same term with respect to Hilbert transformation minus j into a by 2 into del of f minus f naught, and here plus term is taken here. So the Hilbert transformation of the signal xh of t is nothing but Fourier inverse of xh of f term. So substituting this and taking the inverse transformation of the same, we will be getting, after solving this by trigonometric solutions, we will be getting in terms of sine 2 pi f naught t. So this is for the first solution, whereas for the next solution in terms of sinc function. So this is a sinc of t. So for sinc functionality, as I said, will be represented in terms of two terms. One is with the signum function with having a minus and plus value. So we will be taking y of f, that is Fourier transformation of the same, and representing in terms of Hilbert transformation, and finally representing the equation for the given signum functionalities. So here I am taking a signum function of sinc function, which is t. So here in terms of signum functionality, I am going to represent with respect to minus 0.5 to plus 0.5. So the signum function of pi by f is represented with respect to minus j into pi of 2 into f minus 1 by 4, and the same term with respect to f plus term. And taking here y h of t, that is inverse functionality, will be getting these two terms. So what is our next topic is positive pre-envelope. What is positive pre-envelope or a spectrum? We'll be seeing here. Let us consider an x of t signal be a real signal with the Fourier transformation x of f. So if x of t is a function, its Fourier transformation is x of f. So let us define x plus of t as a positive pre-envelope for this signal. So plus represents your positive pre-envelope, and the spectrum for this positive pre-envelope x plus of t is 0 for the negative frequencies, and the proportional to the spectrum x of t for positive frequencies. That is, for positive ranges only it contains a signal, for negative terms it has zeros as a values. So the spectrum of this positive envelope can be represented in terms of x plus of f, that is x of t is taken in terms of x of f, means for the greater than or greater frequencies of 0 it has a value, for equivalent values of 0 it is 0, and for less than 0 is also 0. So this will be the spectrum of the same. So representing here, example, this is your twice the term of x of f frequency, means for frequency f equal to 0 it is 0, and for the remaining terms also it is 0. This is the spectrum of positive pre-envelope. So we can show that x plus of f is equal to x of f plus a signum function. So we know the signum functionality is nothing but having the positive value signal, and for negative it has a negative value, but here for negative it is nothing but not present, so it is simply 0. So we can prove simply x of f plus signum function of f into x of f gives the pre-positive envelope, that is positive pre-envelope. So x of f plus j into signum function of f gives simply the functionality what is present in the positive side of the signal alone. So x plus of t is nothing but x of t plus j term containing with respect to x h of t. So positive pre-envelope examples includes example, if you are considering a cos omega ct signal and a sine sin function of t signals, we will be representing this as two terms with respect to x h of t for this signal, and x plus of t is nothing but which is showing two signals in terms of imaginary axis cos omega ct plus j sin omega ct. So only considering this positive pre-envelope, we will be having the term of e power j omega ct. So y plus of t should be always y plus of f. So what is y of f is nothing but pi of f. Therefore y plus of f will be nothing but 2 pi f minus 1 by 4. So therefore the y of y plus of t will also be Fourier inverse of the functionality y of f. With respect to y of f, here is y plus of f. So substituting the same, we will be getting the same term signals. So what is negative pre-envelope? So similarly, the negative pre-envelope of a signal is nothing but which has the value only for the negative spectrum and it is 0 for the remaining values. So for the positive side, it will be does not have any values. So for here, for negative side, it has the values, and at 0 or frequency 0, it is 0, and for positive greater than frequency is also it is 0. So this will be the spectrum here, which is shown next. So what is bandpass signal is nothing but the signal x of t is a bandpass signal if its spectrum is a non-zero in a frequency range which is contained with fc minus b by 2 less than or equal to frequency term fc plus b by 2, that is frequency ranging between b by 2 f minus or plus, right? So this is your frequency term of minus b by 2 means if it is taken in terms of plus b by 2, so this is the band comprised. So it is the spectrum which contains any non-zero range of frequencies between these two terms. This is the band pass signals. So what is pre-envelope of the bandpass signals? Hope you know the bandpass signal is nothing but it is defined for the terms of whole signal. But what is our pre-envelope, positive pre-envelope signal? We know it is nothing but which is having positive pre-envelope only for the positive side. Hence you could see here for the positive pre-envelope of the bandpass signal will be defined only the positive side of the bandpass filter signals. So what is the positive side of the bandpass filters? So only the positive region is considered, and this shows the positive pre-envelope of a bandpass filter. So what is complex envelope low pass equivalent signal? So we will see what is complex envelope low pass equivalent signal. The complex envelope of a x of t signal example, if the complex envelope is nothing but taking an envelope over the signal and it is represented as x hat of t and its low pass equivalent is given by this, and the spectrum of this x hat signal has the same that of x plus of t which is centered at a frequency f naught. So therefore x hat of t is nothing but x plus of t e power minus j2 pi f omega ct. So which is having the positive spectrum. So we know the positive pre-envelope which is having contained within the positive signal only. With respect to x plus of t, taking Fourier inverse of the same, we will be getting the signal. So it is the range contained between these two equivalents. Hope you understood about this Hilbert transformation and a comparison with fast Fourier transformation. What is Hilbert transformation is very important, and it is asked in 2 marks when giving a two simple questions like find the Hilbert transform of sine omega ct, cos omega ct, etc. And the simple definitions can be asked. So our next topic will be super heterodyne receiver, starting with characteristics of receiver and block diagram of one of the receiver will be explained. Thank you.